So now automatically, as you can see here, it calculated for me my MD. And of course, if I have a table for my deviation survey, I can copy and paste here, okay? And it can be also more points if I want, okay? So I am now describing almost a horizontal well, right? Then I have a liner. I'm assuming that possibly that I can have maybe, you know, my perforation will be at this point, okay? So let's continue. Do I see any questions or chat? Okay. So I have now entered my wellbore description, casings, tubings. I have entered my deviation survey. Now for the heat transfer, I can simply, you know, specify the heat transfer coefficient, all right? Where I can say that, okay, my heat transfer coefficient is 2 BTU per enthalpy per degree Fahrenheit per foot square. Or I can ask the software to calculate that for me. And if I want to do that, then I need to enter the ground density, the ground, conductivity, etc. But let's keep it simple at the moment. And now let's just specify one value, all right? Tubular is done. Downhole equipment, I have only one packer, all right? I don't want to install any of the other equipments. At the moment, I will not add any artificial lift. Now completion. So I need now to drill a completion. So I go here and then I add, drag and drop. I'll put the completion at the liner. Okay. Now it starts to complain because it is missing all the information related to the completion. Click on this one. And now you can see that it is complaining about the reservoir pressure, reservoir temperature, and the productivity index. All this depends on the IPR model that I select. Okay, so there are different ways to describe my IPR models. Each of these models will be used to calculate the drawdown or the pressure drop. Okay, so this can be listed here based on the geometry profile and the fluid entry. Okay, if I say that my geometry profile is horizontal, then it will be turned into the horizontal IPR methods, the steady state and the pseudo steady state methods, Joshi and Babu and Ode. And this is for the single entry, what we call a single entry IPR. Or I can make it distributed, you know, due to Zoom, because I'm sharing and my machine is slow. So if I say distributed entry, then I need to define the starting point, the end point, and now I have now a new method called distributed PI or trilinear transient IPR. Trilinear transient IPR, this is for unconventional resources, for shale formations. So let's go for the simplest now, and let's make it again. Let's make it single point, vertical, and then PI. So the reservoir pressure, let's say the reservoir pressure is 2,800. Reservoir temperature is, let's say, 190 degrees Fahrenheit. The IPR basis is liquid, so productivity index is maybe 5 barrel per day per PSI. Now, these options, I'm going to show you the effect in a moment. So what is still complaining about? It's complaining about the fluid. I have not assigned fluid to the completion. So I go to the fluid model, and then I'm going to click on new fluid. I can add an existing template, like for example, dry gas, light oil and gas, heavy oil and gas. Let's go to light oil and gas and click on OK. Now, this is the template for the fluid, okay? So I define the water cut, the gas oil ratio. Let's say the gas oil ratio is 500 standard cubic feet per septic barrel. This is the gas specific gravity. Let's say it's 0.85. This is the water specific gravity, and this is the API. So let the API, let's make it more practical to be 35. And this is if I have any impurities. This is the viscosity options, calculations, all the correlations for calculating the viscosity. I can even specify my viscosity if I want, you know, etc. If I have any fluid calibration points where I can measure the fluid, let's say I have the formation volume factor, I have the saturation pressure, etc. Or I can still leave these correlations to calculate all these properties for me. No need for calibration. So that's it. I have defined my fluid now. And now there's no validation errors. Now I am ready to run my first case. Okay. So I go to Home, and then I go to Nodal Analysis tab. He will ask me about where do you want to put your node. I tell him bottom hole, because in theory you can put your node at the wellhead, right? Click on OK. And now he's asking me about what is your outlet pressure. Let's say my outlet pressure is 250 psi. And now I click on Run. So this is my beautiful inflow and outflow curves. And this is my intersection point. This is the operating point. And the operating point here is defined by the flow rate and the flowing bottom hole pressure. So the well now should produce 5,784 stock tank barrel per day. And this is in stock tank conditions. This is what I'm going to see at the surface. Okay. And this is the flowing bottom hole pressure. Where? At this point here. As you can see here, this is my nodal analysis point. Okay. Now, let's play with the nodal analysis. So if I tell him now, what is the impact of changing water cut? Remember, as the water cut increases, what will happen to the production? Production will go down. Why? Because the outflow curve will go up. So let us see that. So if I go to completion and I go to the water cut and I say, okay, 0, let's say 25 and 50. And I click on Run. So as you can see here, sorry, I said as the water cut increases, the VAP will go up. Okay, so this is obvious here. When the water cut, you know, we just expand this a little bit. Okay. So this is water cut of 0, all right? And as you can see here, the water cut, by the way, don't be fooled with this inflow. So we're having multiple inflows on the same plot here. Look into the outflow curve. So this is outflow of 0, representing this curve here. And this is the intersection. This is the outflow of water cut 25, and this is the outflow of water cut 50. As you can see here, as the water cut increases, the VLP curve goes up. Not only this, I'm going also to have what we call the profile results. Profile results represents, you know, different curves at different water cut. This is at 0, this is at 25, and this is at 50. As you can see here, the two boundary conditions are the same, but the curves are different because I have different pressure drop, because I have different flow rates. This is the system results, okay? Now, let me do something interesting. So let us go now to the completion. So this is my reservoir. Remember I told you about these checkpoints? So now I have checked by default, use Vogel below bubble point. If I uncheck this will be my straight line, okay? But now in reality, the software will go to my fluid description and understand where is my bubble point. It seems that my bubble point is somewhere here. And then after the bubble point, Vogel will play a role in actually making this curve. This curve behavior, or the deviation from the straight line, will be more severe as the GOR increases. Let me show you. If I go now to the fluid model and I go to override method, I'm going to override the phase ratios. Originally, the phase ratio was 500, correct? So if I'm going to increase the GOR and I say that it is 1500, and I go back to my IPR curve, I see now that it is more curved compared with previous. Okay. Now, we have now something called Vogel water cut correction. So as the water cut increases, then, you know, the water cut is what? Is water compared with oil, okay? As water cut, as more water cut I will have more water than oil. So the effect of gas-oil ratio will become less and less, correct? So you'll notice that if I go now, so look into this curve. I'm going to take a screenshot. Now we'll keep it aside. Now I go to my fluid model. Let me just uncheck the use Vogel water cut correction. So I go now and I make this water cut to be 60%. Look into what will happen now. So the moment I click on Vogel water cut correction, the IPR curve will be a bit different. And let me show you the difference here. See, you will notice that, you know, it becomes straight line, and then, you know, the effect of the gas will become less. This can be also be seen if I go to my nodal analysis again, while this is checked, and then I'm going to leave the same values. Now you'll see now an interesting thing into the inflow also. See now? Now my inflow is also affected by the water cut. So the water cut is not now only affecting my outflow or my VLP curve, it is also affecting my inflow because I checked this option here, right? Any questions so far? So this is what we call the nodal analysis in PipeSim, okay? And as I described earlier, I wanted really to go through this nodal analysis theory to give you flavor of, you know, when PipeSim calculates the inflow and the outflow by using different sensitivities. And I can of course, you know, remove that, and now I can add an outflow sensitivity. Like for example, I can tell them, okay, change for me the outlet pressure, the wellhead pressure. And then the default wellhead pressure 250. So I'll tell them, okay, give me 250, the impact of changing the wellhead pressure, 350, 500, okay? And then let's also make the completion. Let's say I put the water cut of 50, for example. Now you see that because you know, the doesn't allow me because the water cut is actually used in both. Okay, so let's just remove the water cut, and then let's go to the, again, wellhead pressure. So 250, 350, and 550. Okay. Click on run. As you can see here, the outflow is affected directly by the wellhead pressure. What if I change the PI, productivity index, 5, 20, 100. Run. You see now I have all these points here, and then if I want, I can you know, I can zoom. Sorry. I can zoom like this. Still running. See now? These are different outflow curves representing different wellhead pressure. And this is different key inflow curve representing the productivity index. And then I can now later on select my future production, for example, as the water cut increases, as the wellhead pressure increases, as the reservoir pressure increases, etc. And then I can represent it to my management for actual decisions in the field. So now next, let's try to design a pump for this well. Okay, so let's assume now that let's remove everything, and now let's go and you know, change the conditions. So my reservoir pressure has declined. So now the reservoir pressure is 2,100 only. And my water cut actually has increased. Let's say it was 500. My water cut has increased to 70. I am, let's say, 10 years from the first production. Now, if I go to my nodal analysis again, see how much I'm going to produce now. The well is dead for these conditions. See? There is no intersection between the inflow and the outflow. And it says unconverged flow rate. That means the well cannot flow under these conditions. What are these conditions? Again, reservoir pressure 2,100, productivity index 5, and the water cut is 70. The well is dead under these conditions. So now what do I need to do? I need to install a pump that will bring back my production to, for example, let's say 2,000. So how do I do that? I go to ESP design, an interesting task. Click on that. Now it will ask me about the operating conditions. What do you want to do? So I tell him I want the outlet pressure to be 250. This is my reservoir pressure. This is my, so all of this is taken from, you know, the current well conditions. But then I tell him I want to produce 2,000. So this is my desired production. Now, based on this, he automatically told me, okay, I'll put the pump at the end of the tubing. Now I can click on this button to see what are the available pumps that can give you this, that can give me this flow rate. So now I can select, for example, the one that I have a contract with, for example. Well, for the time being, let's use the first one, which is REDA. This is a Schlumberger pump. This is the series, the minimum flow rate, maximum flow rate, and this is the efficiency. When I click on OK, now it says, okay, I will install the pump, but now I need to know how many stages do I need to put. Okay, when I click on run, it will go and calculate for me everything. Okay, so now as you can see here, this is the original IPR. Okay, this is the IPR at different frequencies. Okay, and as you can see here, this is the IPR at 60, where I wanted to produce 2,000. And now the result is 84 stages with 60 hertz. This is good efficiency. This is the power required at the bottom hole. all right? This is the head added by the pump. This is the differential pressure. And now I can look into the actual pump performance curve. So this is the actual pump performance curve. This is the operating conditions, but this is at BBL. This is at flow conditions, right? And now this is the nodal analysis after installing the pump. I'm happy. I can now tell him install the pump. So now click on install the pump. The pump now will be added here. See, it was added at the same depth. All that in simulation, right? This is very important for you. If you are a production engineer, you want to come up with a new ESP design. This is what you need to do. I have defined what is my where do I need to the well to flow, right? And then I selected from the catalog. Now I have installed the pump. Now, if I go to my nodal analysis while the pump is installed, let me just show you. If I go to outflow sensitivity, and I go to the pump, just to see the impact of the pump, I can put two frequencies. Frequency of 0 represents the pump is not rotating. Frequency of 60. And now when I click on run, see now, this is when the pump is not running. This is when the pump is running. And now, as you can see here, why I'm producing more rate. I was expecting to produce 2000 only. So let us see here. Yeah, because you see, it was reading the original reservoir pressure. You should have clicked reset boundary conditions. Again, 250. See, now the reservoir pressure is 2100. Now it should give me the exact rate, which is 2000. See, it is producing 2000. So this is when there is no, when the frequency is 0, when the pump is not running, and this is when the pump is running. Okay. Good. So I think I'm done. So let's open the floor for any questions.